Let's talk about points of inflection. Where your graph changes concavity, it's going to be considered a point of inflection, and rather than writing the whole thing out, we'll just use POI. So if we look back up at our previous problem, let's see, oh, on the other page, I guess it was. We were concave up from negative square root of 1/3 to positive square root of 1/3 and concave down on either side of that. So our points of inflection would have occurred at negative square root of 1/3 and also another one at square root of 1/3. And in order to get the y value to go with them, we'd have to plug that back into the original function. So finding points of inflection then, if a function f has a point of inflection, it occurs at some point x sub 0 where the second derivative is equal to 0. That's how we looked for our boundaries to begin with. Or it doesn't exist. So then your steps for finding your point of inflection. Find the second derivative and then find the values for which it's undefined or equal to 0. Plot them on the number line like we just did, test for concavity. The graph has points of inflection where the graph changes concavity at that point. If no change occurs, then it's not a point of inflection. You could find values for which your second derivative is equal to 0 or doesn't exist, but it's still concave up on both sides or concave down on both sides, so there wouldn't be a point of inflection there. So if they exist, list the coordinates of the extrema and points of inflection, state the intervals on which the function is increasing and decreasing, concave up and concave down. Okay, so there's a lot here. Some of this is coming from our first derivative, and our second, now the rest of it's coming from our second derivative. So let's go ahead and take the derivative of this function. First derivative will be 4x cubed minus 6x squared. Let's get our critical numbers so we can figure out where we're increasing and decreasing. We're going to set this equal to 0. GCF will be 2x squared. Okay, our remaining factor in our parentheses is prime, so we're going to set each factor that contains a variable equal to 0. Now x squared equals to 0 will be the same thing as x equals 0, so that's going to be one of our critical values. And 2x minus 3 is equal to 0 means we're going to add the 3 and divide by the 2. So 3/2 is going to be our other critical value. Let's build our number line. Okay, we can test negative
1, positive 1, positive 2 in our first derivative to figure out increasing or decreasing. So f prime of negative 1 is going to be 4 times negative 1 cubed minus 6 times negative 1 squared, which is going to be negative 4 minus 6 is negative 10. Since we're negative on this interval, we'll be decreasing. F prime of 1 will be 4 times 1 cubed minus 6 times 1 squared, so 4 minus 6 will be negative 2. Again, negative, so we're still decreasing. F prime 2 squared will be 8 times 4 is 32, 6 times 4 is 24, 32 minus 24 will be 8. So we're positive, so now we're increasing. They didn't ask us this, but we went from decreasing to increasing, so therefore we have a local minimum at x is equal to 3/2. Let's do our second derivative. Second derivative will be 12x squared minus 12x. I'm going to set that equal to 0. GCF will be 12x. So therefore, potential points of inflection will be at x is 0 and at x is 1. Build our number line. And we'll test -1, positive 1/2, positive 2 in our second derivative to see where we're concave up, concave down. F double prime of negative 1 will be 12 times negative 1 squared minus 12 times negative 1. This will be positive 12 plus 12 will be 24. So we will be concave up on this interval. F double prime of 1/2 okay, 1/2 squared will be 1/4. 1/4 of 12 will be 3. 1/2 of 12 will be 6, so 3 minus 6 will be negative 3, which means we're concave down on this interval. And our last test point's 2. 12 times 2 squared minus 12 times 2 will be 48 minus 24 is 24, so it's positive again, which means we're going to be concave up again, which means we have 2 points of inflection, one that occurs when x is 0, one that occurs when x is 1. As far as the question is concerned, they wanted intervals on which the function is increasing, decreasing, concave up, or concave down. So for increasing, your intervals is going to be from 3/2 to positive infinity. And for decreasing, your interval is going to be negative infinity to 3/2. For concave up, interval is going to be from negative infinity to 0, and then from 1 to infinity. And concave down will be between 0 and 1. Okay, these are things now that help us draw a much better picture by hand than we could in college algebra. So in college algebra, we determined the domain, we found x-intercepts and y-intercepts by letting x's be 0 and y's be 0. We determined symmetry to kind of help us out, even, odd, or neither. So if we plugged in a negative x into our function and none of the signs changed, then we were considered to be even, which is symmetrical over the y-axis. If all of the signs changed, then we were considered to be odd, which means we're symmetrical over the origin, so kind of diagonal. And then some did, some didn't, then you just weren't symmetrical over either one of those things. And we also determined end behavior by using your leading coefficient test. So if the degree of your function was even, then you were rising to the left and right or falling to the left and right. If you were odd, you were going in opposite directions. And that was determined, whether you're rising or falling, by the sign on your leading coefficient. So if your leading coefficient was positive and your degree was even, then both ends were rising. If it was negative, both ends were falling. If you were odd and your leading coefficient was positive, you were falling left and rising right. And if you were negative, you flipped over and you were rising left and falling right. So now in calculus, we can get a better picture of some of the things we used to have to guess at before. We can go ahead and differentiate to determine intervals on which the graph's increasing and decreasing and where those relative extremas are. Before, we knew between two x-intercepts that it had to turn around somewhere, but we weren't aware of where that would happen. This is how we figure out where that's going to happen. And then the second derivative test kind of helps us give us that little point of change where it might go from concave down to concave up to make our graph much better, which are these points of inflection. So we're being asked to graph this function, negative x cubed plus 3x minus 2. If you know about your parent graph of x cubed, you have an idea as to what this is going to look like. You know it's leading with a negative and it's odd, so it's going to be rising to the right and falling to the left. I know it's doing that this way and this way at the end. But let's go ahead and figure out what our y-intercept is. So if I do y is equal to negative 0 cubed plus 3 times 0 minus 2, that'll be negative 2. So our y-intercept is at 0, -2. Go ahead and plot that. X-intercepts. Well, potentially we have 3 x-intercepts. However, unless we start going for rational zero theorem in testing, we're not going to be able to find the x-intercepts, or we could plug it into our graphing calculator and get them. But let's just say right now, since we can't graph it by eye, excuse me, we can't factor it by eye, we're just going to leave x-intercepts alone. So we want to figure out where we're increasing, decreasing, and local max min values. So let's go ahead and do our first derivative. So first derivative will be -3x squared plus 3. Set that equal to 0. We're going to take out a -3 as our GCF. Just going to leave us with x squared minus 1 inside the parentheses. Difference of two perfect squares, so again, product of a sum and difference, which means critical numbers will be x is equal to -1 and x is equal to +1. All right, let's do test values. We use -2, 0, +2. So then f prime of -2 will be -3 times -2 squared plus 3, which will be 4 to -12 plus 3 is going to be -9. So it's negative, which means we're decreasing. We'll do f prime of 0. -3 times 0 squared plus 3 will be 3, so it's positive here, so it's going to be increasing on this interval. And f prime of 2 will be equal to -3 times 2 squared plus 3, which again will be -9. So negative means we're decreasing again. Since we went from decreasing to increasing and increasing to decreasing, we have a local max and a local min. So we've got a local max at, now notice I use this f prime notation. Let's go ahead and call this f of x so that we can make that notation okay. So then our local max will be at f prime of 1, which will be -1 cubed plus 3 times 1 minus 2, which is going to be 0. So as it turns out, there we go, we found one of the x-intercepts at 1, 0, right there. And we're going to have a local min at f of -1, which will be -1 cubed plus 3 times -1 minus 2. So -1, opposite of that, +1, 1 minus 3 will be -2, -2 minus 2 will be -4. So then let's put that point on our graph, -1, 1, 2, 3, 4, -4. Okay, now I want you to note that if this guy is a local max, that meant we turned around there. If you remember back to your college algebra, you talked about multiplicities. And if your multiplicity in factored form gave you an x-intercept, was an even multiplicity, that meant it touched and turned or it bounced. So the factor of x minus 1 would be x minus 1 squared if we went to factor this guy. Okay. That being said, let's look for concave up, concave down. And points of inflection. In order to do that, I have to take the second derivative, so let's stick with the f prime notation. So f double prime of x will be, we've got -3x squared plus 3, it'll be -6x. If we set that equal to 0, then x is equal to 0 is our only potential point of inflection. let's test -1 and +1. So then f double prime of -1 is going to be -6 times -1, which is +6. So we're concave up on the left. And f double prime of +1 will be -6 times 1 will be -6. So we're negative on this side when we concave down on the right, which means at x equals 0 we have a POI. And f of 0 will be -0 cubed. Actually, we know this is the y-intercept, but -0 cubed plus 3 times 0 minus 2, which is equal to -2. And we already have that plotted. Okay, so that means on this particular graph, we're concave down on this side, so, and concave up on this side. These are hard to draw. You'll get the, perhaps you're more of an artist. Okay, so it has that little kind of an S curve in there. All right, we have all these things, so now in order to get a nicer picture, we could throw in a couple of other numbers, come up with some x values, how sharply is this falling and rising after we get to the right of 1 and the left of -1. So let's go ahead and do f of -2, which would be a -2 cubed plus 3 times -2 minus 2, which is going to be, let's see, this would be -8, +8, minus 6 would be +2, 2 minus 2 would be 0. Another x-intercept. So there it is. And if we do f of +2, it'll be the opposite of 2 cubed plus 3 times 2 minus 2, which will be -8 plus 6 will be -2 minus 2 will be -4. So 1, 2, 3, 4. All right, so then falling and rising quite steeply. So that's approximately what our graph will look like. All right, so if we wanted to do factored form, since we're leading with a -1 and we know what our intercepts are and we know the multiplicities, because at most you can have 3 factors, that one bounced, that one crossed through, so even in odd multiplicities, the negative sign will flip the graph over, which is why it's rising to the left and falling to the right. So x minus or x plus 2, sorry, x plus 2 would be this factor, and then that factor would be an x minus 1. But since it bounces and your multiplicity is 3, it would be squared. And I don't expect you to do that, but I just wanted to point that out from your college algebra. All right, let's do one more of these. So I have f of x is equal to -3 times the quantity of x minus 2 to the 2/3 power plus 3. If your index is odd, that means your domain is -infinity to +infinity. If this index had happened to be even, we would not have been able to use values that made your radicand negative. It's okay to be 0, it's not okay to be negative. All right, let's start with our y-intercept. Let x be equal to 0, so f of 0 is -3 times 0 minus 2 to the 2/3 power plus 3. If you put this in your calculator, it's approximately -1.76. Okay, if we want to find x-intercepts, we're going to let y be 0. So now -3 times the quantity x minus 2 to the 2/3 power plus 3 will be equal to 0. So then let's go ahead and subtract 3 from both sides. And we'll divide both sides by -3. All right, I want to undo the exponent, which means I need to raise it to its reciprocal. so that when I multiply them, they equal 1. So we're going to raise both sides to the 3/2 power. Now, when we do this, on the left-hand side, we have x minus 2. On the right-hand side, this is the square root of 1 cubed, which means we're going to have to use two values, because when you take the square root, it's a plus minus. And when you cube a positive 1, it's a positive 1. When you cube a negative 1, it's a negative 1. So on the right-hand side, it's going to be a plus minus 1. And remember, because this is right, which gave you plus minus 1 cubed, which is where these are coming from. All right, so then we've got x is equal x minus 2. Let's write the whole thing. Is equal to negative 1. X minus 2 is equal to positive 1. If we add 2, x will be equal to 1. X will be equal to 3. Those are your x-intercepts. So let's plot these. Negative 1.76 will be approximately here. 0, negative 1.76. And then we have 1 and 3 for x-intercepts. Okay. For the next step, let's figure out where we're increasing and decreasing, where we might have local max, local min values. So we need a first derivative. Okay, we have chain rule situation here, right? We do this first derivative, so it's going to be 2/3 times negative 3, which means the 3's will cancel. This will be on negative 2, times x minus 2 to the 2/3 minus 1 will be x minus 2 to the negative 1/3. Derivative of the inside will be 1. Derivative plus 3 is 0. Okay, so if we rewrite this, it's going to be negative 2 over, and change this to radical notation. So we either have to figure out where this equals 0 or where it doesn't exist. And for this particular case, it does not equal 0 ever. However, in the denominator, if x is 2, 2 minus 2 would be 0, and something over 0 is undefined, so I don't exist when x is 2. So that's going to be my critical value. And we'll go for positive 1, 1 and 3 for test points. First derivative evaluated for 1 will be negative 2 over cube root of 1 minus 2. 1 minus 2 is negative 1. Cube root of that is negative 1. Negative 2 over negative 1 is positive 2. So we're increasing on the left. If we use a 3, minus 2 is 1. Cube root of 1 is 1. Negative 2 divided by 1 is negative 2. So we're negative on the right, which means we are decreasing. Which means we went from increasing to decreasing, so we have a local max at 2. And let's go ahead and evaluate that in our original function. Two minus 2 is 0, 0 to the 2/3 is 0, negative 3 times 0 is 0, plus 3 is 3. So our 0.23, we will graph that, 2 over and 3 up. All right, so now we have concavity to do. That means we need a second derivative. So here is our first derivative. So our second derivative is going to be negative 1/3 times negative 2, which will be positive 2/3, times x minus 2 negative 1/3 minus 1 will be negative 4/3, times over the inside, which is the 1 again. So this is going to be the same situation. If I wanted to rewrite this, 2 over 3 times x minus 2 to the 4/3 power, or we could write it as the cube root of x minus 2 to the 4th. So that does not exist, again, where x is equal to 2. Let's go ahead and test for concavity on either side of this. So on the left side we'll use 1, on the right side we'll use 3. Second derivative evaluated at 1, 2 over 3 times 1 minus 2 to the 4/3. So 1 minus 2 is negative 1. Cube root of negative 1 is negative 1. Negative 1 to the 4th is positive 1. So this is just 2/3. We're positive. So we're concave up on the left. F double prime of 3 will be 2 over 3 times 3 minus 2 to the 4/3 power. 3 minus 2 is 1. 1 to any power is itself. So this is positive 2/3 again. So we're still concave up, even though we have a local max at that same point. We're concave up on both sides of that, which is interesting. So then, let's go ahead and get a couple extra values, and then we'll draw our picture. So we're going to do f of 1, 2, 3, 4. So f of 4 will be negative 3 times 4 minus 2 to the 2/3 plus 3, which will be equal to, when you put in your calculator, approximately negative 1.76. So 4 over and 1.76 is here again. And f of, say, negative 1 equal to negative 3 times negative 1 minus 2 to the 2/3 plus 3. In your calculator, it's going to be approximately negative 3.24. So negative 1, negative 3.24 is here. So this graph's concave up on both sides. Looking something like that. Okay, problems like this can be found in your textbook on page 217, numbers 9 through 46.